The Bernoulli random variable, such a useful construct. Any binary outcome can be modeled with this random variable. Here we model whether an order at this Massachusetts ice cream stand is delivered within 3 minutes. The owner considers that a fast order. Using our language of random variables, we create the graphical model and accompanying statistical model to capture this real-world scenario inside of our math world representation. As we go further, we are also going to want a computer world representation of the scenario so that we can automate inference computations using Bayes' rule. The Causac package that we will use in R adopts a representation of real-world scenarios called the Generative DAG. The Generative DAG combines the ovals that most business stakeholders can understand, along with a way of conveying the mathematical recipe for generating a random variable that our computers understand. At this point, this representation on the right here should feel like a natural extension to what you've learned. A generative DAG is a recipe for simulating real-world data realizations. In the lower right, we see an oval representing a single real-world observation of whether a customer order was a fast order. The recipe is clear on how we might generate it. Using a function from the Causac package for generating a Bernoulli random variable, we execute one draw of the recipe, n equals 1, with success probability of 70%. Our first execution of the recipe gets us a 0. The order was not fast. Our second execution also led to a slow order, but then hitting Control-Enter a few more times yields 2 successful fast orders. To represent more than a single realization of a set of random variables, you indicate that a scenario has more than one realization by enclosing the random variable or variables in a plate, basically a rectangle. The number in brackets, in this case the 3, indicates 3 realizations of the random variable are observed. Within R, we can change the n arguments value from 1 to 3 and get our 3 realizations of x using the recipe shown in the bottom right. In real-world scenarios, we often want to estimate the probability of success. It is unknown. While we can replace the 70% success probability with a variable, let's call it theta to be fancy like the Greek letter-using mathematicians who prefer Greek letters to Arabic letters when representing parameters of distributions. The problem with this DAG is it is not a generative DAG because we have no recipe anymore for generating a draw of x. Without a way to get a theta value, we are stuck. So whenever you have undefined variables for a node on the right-hand side of the math line, like theta, you need to make that variable a parent node and define how it gets generated. In this case, we create a single realization parent node called theta that represents the success probability which each of the 3 observations of x will be generated. Simulating this in R involves creating an R object to store the value of theta. In this case, we see a draw of theta got a value around 74%. And then using this draw, 3 realizations of x get generated. In this case, all fast orders. In data analysis, our job is to get insight from the real-world observations. To indicate that we have observations or data for certain nodes of the generative recipe, a darker fill color is used. In this generative DAG, we have observed whether 3 orders were fast or not. Our initial uncertainty, aka our prior uncertainty, is that theta can be any number between 0 and 1. However, once we learn to automate Bayes' rule, we will eventually get a posterior distribution of theta that is no longer uniform, but shaped to reflect the balance of prior and likelihood components specified from this generative recipe. Notice the theta node expresses prior uncertainty and the x node, because it is observed, expresses the likelihood for a given theta value. To bring in one more wrinkle, let's look at this generative DAG where theta is now included inside of the plate. Without the plate, we would just have one value of theta and one value of x. Now the plate suggests we replicate draws of the theta and x pair 3 times. Inside of R, we can just wrap the code for generating a single theta x pair inside of a for loop that executes the logic 3 times. Previously, we had used 1 theta, and that 1 theta was used to generate all 3 realizations of x. But now we do 1 theta generates 1 x and repeat this pair creation 3 times. One last quick note is that in the R world, functions often work when you pass vectors as inputs, not just single number scalars. Learning to think using vectors is helpful as most R coding takes advantage of R's extensive vector handling capabilities. So here, we can save theta as a vector of 3 values, and then when we pass that vector to rburn, it will generate a single draw for each of the 3 values of theta using less lines of code than the for loop. You have now been exposed to the simple building blocks of generative DAGs. As we progress, these generative DAGs will become bigger, more expressive, and more informative. As you can imagine, presenting all this technical jargon to non-technical people just adds visual clutter. Luckily, we will learn to present